Welcome! In this video, we'll be diving into the world of trigonometric equations. By the end of this lesson, you will be able to solve these equations using two different methods. First, you'll learn how to solve them graphically using a graphing utility. Second, you'll master the analytical approach using algebraic techniques and your knowledge of the unit circle. Trigonometric functions like sine, cosine, and tangent are many to one. This means that for a single output value, there can be multiple input values. For example, if we have sine of x equals 0.5, there isn't just one answer. If you look at the graph of the sine function, you can see that the horizontal line y equals 0.5 intersects the curve over and over again, infinitely. Within the interval from 0 to pi, there are two solutions, x equals pi over 6 and x equals 5 pi over 6. If we expand the interval, we find even more solutions. Our goal today is to learn how to find all solutions within a given interval. Let's begin with our first objective, solving trigonometric equations graphically. This method is powerful when you have access to a graphing display calculator or GDC. We'll treat the equation as two separate functions and find where their graphs intersect. Let's look at a real-world example. Imagine the depth of water in a harbor, d, is modeled by the function d equals 3 times cosine of pi over 12 times t plus 8, where t is the time in hours. We want to find the times at which the depth of the water is exactly 9 meters. This gives us the equation 9 equals 3 cos pi over 12t plus 8. To solve this graphically, we'll graph two separate equations. The first is the function for the water depth, and the second is the constant depth we're interested in. On our calculator, we'll set y1 equal to our function, using x instead of t. So y1 is 3 cos pi x over 12 plus 8. Then we'll set y2 equal to 9. Now let's graph these. We see our cosine wave, representing the changing water depth, and a horizontal line at y equals 9. The solutions are the x-coordinates of the points where these two graphs intersect. Using the calculator's intersection feature, we find the first intersection at approximately t equals 4.702 hours, and the second at t equals 19.298 hours. Often we need to convert the decimal part of the hours into minutes. We do this by multiplying the decimal by 60. For the first time, 0.702 times 60 is about 42 minutes. For the second, 0.298 times 60 is about 18 minutes. So, the water depth is 9 meters at approximately 4:42 and 19:18. So, we've seen how to find solutions graphically by finding the intersection points of two functions. This method is very reliable, especially for complex equations. Now let's move on to our second objective, solving trigonometric equations analytically or by hand. This requires us to use inverse trigonometric functions and our understanding of the unit circle. We'll start with the sine function. Here's the general method for solving sine equations. First, find the principal solution using the inverse sine function. Second, find the second solution in the first cycle using the identity that sine of x is equal to sine of pi minus x. Finally, since the sine function has a period of 2 pi, we can find all other solutions by adding or subtracting multiples of 2 pi to our first two solutions. Let's apply this to an example. We need to solve sine of x equals the square root of 2 over 2 in the interval from 0 to 5 pi over 2. First, we find the principal solution. We should recognize root 2 over 2 as a standard value from our unit circle. The principal value, x1, is the inverse sine of root 2 over 2, which is pi over 4. This is our first solution. Next, we find the second solution using the formula pi minus x1. Our second solution, x2, is pi minus pi over 4, which simplifies to 3 pi over 4. This is also within our interval. Now, we need to check for any other solutions in the interval 0 to 5 pi over 2 by adding 2 pi to our initial solutions. Let's visualize this with a graph. Sketching the graph of sine and the line y equals root 2 over 2 helps us see how many solutions to expect. We can see our first two solutions, x1 and x2. Notice the graph intersects the line a third time within our interval. This third solution comes from the periodic nature of the sine function. We find this third solution, x3, by adding 2 pi to our first solution, x1. So x3 is pi over 4 plus 2 pi, which equals 9 pi over 4. This value is within our specified interval. If we tried adding 2 pi to x2, we would get 3 pi over 4 plus 2 pi, which is 11 pi over 4, or 2.75 pi. This is outside our interval, so we stop. Therefore, the three solutions to the equation sin of x equals root 2 over 2 in the given interval are pi over 4, 3 pi over 4, and 9 pi over 4. Next, let's look at how to solve cosine equations analytically. The process is very similar to solving sine equations, but with a slight difference in finding the second solution. For cosine, after finding the principal solution x1, the second solution is found by calculating 2 pi minus x1. This is because cosine is an even function, meaning cos of x equals cos of negative x, and negative x is coterminal with 2 pi minus x. Just like with sine, we find all other solutions by adding or subtracting the period, 2 pi. Let's work through an example using degrees. We need to solve cosine of theta equals 0.5 for theta between negative 360 and positive 360 degrees. First, the principal solution. The inverse cosine of 0.5 is 60 degrees. This is our first solution, theta 1. The second solution, theta 2, is 360 degrees minus our first solution. So, 360 minus 60 gives us 300 degrees. Both 60 and 300 are in our interval. Now, let's check for other solutions. Our interval includes negative values, so we should subtract 360 degrees from our initial solutions. A quick sketch of the cosine graph from negative 360 to 360 shows us that we should expect 4 solutions in total. We found the 2 positive ones, so let's find the 2 negative ones. To find the remaining solutions, we subtract 360 degrees from our first 2. Theta 3 is 60 minus 360, which is negative 300 degrees. Theta 4 is 300 minus 360, which is negative 60 degrees. Both are within our interval. So our 4 solutions for theta are negative 300 degrees, negative 60 degrees, 60 degrees, and 300 degrees. Finally, let's cover how to solve tangent equations. The method for tangent is simpler because its period is pi, not 2 pi. To solve a tangent equation, you find the principal solution x1 using the inverse tangent. Then, because the period of the tangent function is pi, you can find all other solutions by simply adding or subtracting multiples of pi from x1. Let's see this in action. We will solve tangent of theta equals negative square root of 3 for theta between 0 and 2 pi. First, we find the principal solution from the calculator. The inverse tangent of negative root 3 gives us negative pi over 3. Now take a moment to consider this result. Is negative pi over 3 in our required interval of 0 to 2 pi? No, it's not. However, this principal value is still the key to finding the solutions that are in the interval. Let's sketch the graph. We can see the principal value at negative pi over 3. We need to find the corresponding positive angles that have the same tangent value. We do this by adding multiples of pi to our principal value. First, let's add pi. Negative pi over 3 plus pi gives us 2 pi over 3. This is our first solution in the interval. Next, let's add 2 pi to our principal value. Negative pi over 3 plus 2 pi gives 5 pi over 3. This is our second solution. If we were to add another pi, we would get 8 pi over 3, which is outside the interval of 0 to 2 pi. So we have found all the solutions. The solutions to tan theta equals negative root 3 in the interval from 0 to 2 pi are 2 pi over 3 and 5 pi over 3. Sometimes, trigonometric equations involve transformations inside the function, like a horizontal shift or a change in period. We can handle these using a substitution. The key idea is to substitute the inner part of the function with a new variable, solve for that new variable, and then substitute back. Let's look at an example. We need to solve cosine of the quantity x plus 40 degrees equals root 3 over 2 for x between 0 and 360 degrees. The expression inside the cosine is x plus 40 degrees. Let's substitute this with a new variable, say a. We'll let a equal x plus 40 degrees. This simplifies our equation to cos a equals root 3 over 2. This is a crucial step. When we change the variable, we must also change the interval. Since a is x plus 40, we add 40 to all parts of our original inequality. This gives us a new interval for a, from 40 degrees to 400 degrees. Now we solve cos a equals root 3 over 2 for a in this new interval. The principal solution for a is 30 degrees. The second solution is 360 minus 30, which is 330 degrees. Now, let's check these solutions against our interval for a, which is 40 to 400 degrees. Notice that 30 degrees is not in this interval. However, 330 degrees is. Let's look at the graph. We can see that the principal solution a1 is outside our interval, but we can find another solution by adding 360 degrees to a1. This gives us a third possible value for a, which is 30 plus 360, or 390 degrees. Both 330 and 390 are within the 40 to 400 degree interval. So these are our solutions for a. The final step is to convert back to our original variable, x. We use the relationship x equals a minus 40. For a equals 330, x is 290 degrees. For a equals 390, x is 350 degrees. Both of these values are in our original interval for x, so our final solutions are 290 degrees and 350 degrees. Sometimes an equation contains more than one trigonometric function. In these cases, our first goal is to use a trigonometric identity to rewrite the equation in terms of a single function. A common identity we'll use is the double angle identity for sine. Let's solve for sine theta cosine theta equals 1 for theta between negative pi and pi. The expression sine theta cosine theta should remind us of the double angle identity for sine. Recall that sine of 2 theta is equal to 2 times sine theta cosine theta. We can use this to simplify our equation. We can rewrite 4 sine theta cosine theta as 2 times the quantity 2 sine theta cosine theta. This allows us to substitute sine 2 theta, giving us 2 sine 2 theta equals 1. Dividing by 2, we get sine 2 theta equals 1/2. Now we have an equation with a transformation. Just like in the last scene, we'll use a substitution. Let a equal 2 theta. Our equation becomes sine a equals 1/2. We must also change the interval. Multiplying by 2, our new interval for a is from negative 2 pi to 2 pi. Now, we solve for a. The principal solution for a is pi over 6. The second solution is pi minus pi over 6, which is 5 pi over 6. Both are in our interval for a. Since our interval for a is quite large, from negative 2 pi to 2 pi, we must check for more solutions by subtracting 2 pi. Subtracting 2 pi from a1 gives negative 11 pi over 6. Subtracting 2 pi from a2 gives negative 7 pi over 6. Both of these are also in the interval. So we have 4 solutions for a. Finally, we convert back to theta. Since theta is a divided by 2, we divide each of our 4 solutions for a by 2. This gives us our final answers. All 4 of these values lie within our original interval of negative pi to pi. This process of using an identity and then a substitution is a very common strategy. Let's tackle a more complex quadratic problem, one that requires an identity before we can solve it. We need to solve 2 sine squared theta equals 2 cosine theta plus 1. The problem here is that we have both sine and cosine in the same equation. Our goal is to get the equation in terms of a single trigonometric function. We can do this using the Pythagorean identity. Remember that sine squared theta plus cosine squared theta equals 1. We can rearrange this to say that sine squared theta is equal to 1 minus cosine squared theta. Let's substitute this into our equation. Replacing sine squared theta gives us 2 times the quantity 1 minus cosine squared theta equals 2 cosine theta plus 1. Now we have an equation entirely in terms of cosine. Let's simplify and rearrange it into standard quadratic form. First, distribute the 2 on the left side. Then, move all terms to one side to set the equation to 0. This gives us 2 cosine squared theta plus 2 cosine theta minus 1 equals 0. This quadratic doesn't factor nicely. The textbook shows a factored form, which seems to be a typo, as 2y1 y plus 1 would give 2y squared plus y minus 1. Let's assume the intended equation was 2 cos squared theta plus cos theta 1 equals 0. Let's solve that one instead, as it matches the factorization. Assuming the intended quadratic was 2 cos squared theta plus cos theta minus 1 equals 0, this factors into 2 cos theta minus 1 times cos theta plus 1 equals 0. This gives us two separate equations to solve. Cosine of theta equals 1/2, and cosine of theta equals -1. Now we solve each of these for theta in the interval 0 to 360 degrees. For cosine theta equals 1/2, the principal solution is 60 degrees. The second solution is 360 minus 60, which is 300 degrees. For cosine theta equals -1, the principal solution is 180 degrees. In the interval 0 to 360, this is the only solution. Combining our results, we find three solutions in the given interval: 60 degrees, 180 degrees, and 300 degrees. Let's recap what we've learned today. We've explored how to tackle trigonometric equations, which often have multiple solutions due to the periodic nature of trig functions. We started by achieving our first objective, solving equations graphically. We saw that finding the intersection points of two functions on a calculator is an effective strategy. Then, we moved to our second objective, solving analytically. We developed a systematic approach for each of the main trigonometric functions. For sine, we find the principal solution and pi minus that solution. For cosine, it's the principal solution and 2 pi minus it. For tangent, we just need to add multiples of its period, pi. In all cases, we must use the period to find all solutions in the given interval. We also learn how to handle more complex cases. We use substitution to manage transformations inside the function, remembering to always adjust the interval. We used identities to simplify equations with multiple trig functions, or to create quadratic forms. And finally, we solved those quadratic equations by factoring and checking for impossible solutions. Mastering these techniques will provide you with a powerful toolkit for solving a wide range of problems in trigonometry and beyond. Thank you for watching.